So hi, I'm Tom Caswell. I'm currently at NSLS2, where I was one of the initial authors of the Bluesky set of tools. Um, and I guess today I'm going to give you a uh, whirlwind tour of why we did this and kind of where the set of the tools are and our mental model of how they work and what our intentions were. And how hopefully we can see how these can be adapted to electron microscopy. Um, so nice. This is actually an interesting personal connection for me. What I did as an undergrad, I worked my senior thesis. I worked with Saul Gruner and David Miller at Cornell on the adapting one of Saul's X-ray detectors for use in an electron microscope, which has now been commercialized as the EM pad by Thermo Fisher. And if you go to slide 3, there's some pictures from that work. Just it's just fun to come back to this, even though I've wandered off and done soft metaphysics and now have come back to X-rays. It's fun to have the connection back to electron microscopy. So, can you go to slide 5, please? Um, so when you're managing a fleet of instruments or supporting a fleet of instruments, the challenge is you need to deliver reliable solutions that work, that do what is needed for the users, but also as the requirements and needs of the instrument change over time, you need to be able to quickly adapt to those changes and deliver new capabilities very quickly. Next slide, please. At NSLS2, which we're a user facility, so we have beamline staff who work at the facility, whose job it is to the care and feeding of the beamline, and then supporting these external scientists who come in, who provide do the actual science that we do here. And the beamline scientists are extremely good at inventing new things that the instrument needs to do to unlock new capability for the users. Next slide, please. And we found that the external, the users come in and actually do the science are also really good at coming up with new things. And and this creativity is what drives science forward. And we want to make sure that as we build out the control system, in addition to being reliable and robust, we don't stifle that creativity or make it impossible to do the next new and interesting thing. Next slide, please. One challenge that we've gone through in the synchrotron community specifically is that we have a history going back 50 years. The apocryphal, the story is that at NSLS1, some of the critical machinery on the beamline was adjusted with like literally brake cables from a bike, because you just needed to a wire that you could run through the labyrinth, and adjust it a little bit to move the slits in and out. We are now we no longer are. The amount of sophistication and complexity on the beamlines has gone up remarkably. We now have thousands of devices in the beamline, and all of them are computerized. All of them are motorized and controllable via the network. Next slide, please. And so we're going through this transition. We're going from bike cables to a space telescope like level of complexity. So next slide, please. And so how do we cope with this challenge of this rapid increasing complexity and the broad breadth of things that we need to do at the synchrotron across all the different beamlines? So one, we try to apply sound planning engineering, so that just make the things that need to be robust and solid, make them so. Providing good abstractions. There are things that that are different from to support the science, but from the control system point of view, you can simplify them and reduce a lot of that those differences to a small handful of classes that you can handle more reliably. And then finally, collaboration, right? This is a big enough problem that a single facility really can't handle it by themselves anymore. Next slide, please. So part of this is just making sure we do the basics right. In our case, the a change from NSLS1 to NSLS2 is we planned the number of cables ahead of time, and just like the boring, but boring is not the right word. The things that at the foundation you just have to get right. Next slide, please. And making sure we identify where the complexity of the things we want to build is, and how we pull in the right expertise from different different subject matter experts at different times. Right, the analogy here is that you can, throwing together a doghouse is pretty straightforward. That's the thing you the analogy for a control system is that's what a typical scientist would be able to put together. But if you want to build a full house that is rated for human occupation, you need to bring in a lot of external expertise. Next slide, please. Second, we've gone all in on abstractions, both at the control system level and at the high levels. This is the canonical spherical cow, and while these do, they obviously smear out a lot of the things that make any individual device specific. If we can find these abstractions to use and then work against those, and then tune the wrapping of any given piece of hardware to match that abstraction, we found we can get a lot of mileage out of that. In our case, next slide, please. In our case, in NSLS2 and a number of the other synchrotrons, we're using EPICs, which is, fun fact, it came out of the SDI program, the ballistic missile defense program, in the 80s. Next slide, please. My understanding is that there's with Urshkart, there's been some early work on putting Pytango in front of Tango in front of microscopes, to provide the similar thing EPICS provides for the synchrotrons. Next slide, please. And some recent work. Oh, sorry. I wanted the animation on that slide. Sorry. This will allow integration into the rest of the OFID and Bluesky stack very directly, thanks to some work primarily out of Diamond Light Source in the UK, that has a new version of OFID that speaks to both EPICS and Pytango. Next slide, please. And that in both cases, these control systems smooth over a lot of the details of the specific hardware and brings it to some standard. So you can ask. Sorry, I apologize. I'm a bit flustered by the chaos getting ready. These control systems smooth over the exact details of the hardware. And so if you say, what is your voltage, depending on what device that is, what vendor it came from, exactly how you get that is very specific. But there's a layer that goes from the hardware details to I have a value on the network that I can query and get the value, set the value, and ask to be notified when it changes. And with that level of detail, you can actually get very far with building layers on top that work. Next slide, please. And then on top of that core layer of the control system, Bluesky is a orchestration layer that lets you say, this kind of provides MATLAB-like functions, right? So you can say, I have something I can scan that I want to move in a grid pattern, over this range of things with these resolutions, use these detectors, then please write it down, please record it with this sample name, and some metadata about what's going on at the beamline and why you're looking at the sample. And this allows us to separate the writing of those plans to robustly capture, run that scan from the details of exactly what hardware we want to do it with. So you can write the plan once and then reuse it many times with many different hardware. This could be the same hardware on either at the same facility or at a pure facility that has the same capabilities but with different hardware underneath. Next slide, please. Once we've collected the data, we now, tiled is is a unified data access layer that we've developed. As core data, tiled is a data catalog. However, instead of providing a location of the file where the data is, it serves you the data directly. So if you have a HDF5 file or a directory of TIFFs representing some scan, you can ask tiled for the fifth frame of that scan, and then it will serve it to you in whatever format the client can handle. So if you're a Python or C program who can handle C buffers, it will send you the data directly. But if you're a web app that wants JPEGs, it will serve it to you as a JPEG. Next slide, please. And then the third tool we use is collaboration. This is being used across a number of light sources around the world. And as I mentioned before, there's some initial work to bring this to electron microscopes as well. Next slide, please. And something we did from the very beginning is we did not release Open and Bluesky when they were done. We put them on GitHub in the open basically from day one. We keep some of our site-specific details and credentials internal, which the slide says they're boring, but we hope they're boring, but they might be very exciting to people we don't want to have them. And because we do this, because we have the libraries and all the planning and work around those libraries open, that means people can and do reuse and repurpose that work with relatively low cost to us. And we benefit quite a bit from making connections and making friends to build these collaborations, learning what other people do with this and what their needs are, and how very frequently we found our peer facilities at synchrotrons, if they say, oh, Bluesky's great, but it can't do X, we'll discover that there's some beamline that at NSLS2 that has that same need that either we haven't had time to get to, or we haven't had that conversation with the beamline scientist yet, and that now we're benefiting from that exchange of ideas. And it's going to be more and more true that the connections we've built have now had capabilities that are in fact coming back to us as implementations that we've been able to reuse. Next slide, please. This work in the open is actually quite old, even if we don't always practice it as widely as we could. This is an announcement for a open source open science conference held at Brookhaven in 1999. Next slide, please. Fortunately, collaboration is becoming much easier than it used to be. Part of this is GitHub makes sharing code and collaborating on the code much, just technically easier. You don't have to email tarballs around. It's, it's in version control, and we can engage with it. And as one of the very narrow silver linings of the COVID pandemic is that we're all now very good at Zoom, and I am, here talking to you remotely, which 10 years ago probably would not have been a thing we did regularly. Next slide, please. In addition to GitHub, we have a chat community. We've moved to Matrix from Mattermost, but this is being around the world. It basically runs 24/7. So if you're interested and joining that chat, please do. I don't have the link on here, but if you email me, or I can get that to you who want it. Next slide, please. Something that we've been able to do, built on all, based on all these tools we have, is we've demonstrated the ability to use Bluesky to drive two beamlines simultaneously, where there was an AI sitting between them that, looking at the fast probe on the powder diffraction beamline, was able to identify regions of interest to drive the slow beamline to do a more detailed study of particular parts of a sample. In this case, we had two identically grown combinatorial wafers that were registered, so you could basically do the measurement simultaneously anywhere on the wafer. And this was made possible because of the solid engineering of the base and the abstractions that were provided that made these beamlines, that are very different techniques, interchangeable and controllable with the same language. Next slide, please. And again, this reality of these facilities, and I'm going to project and assume the electron microscopes have a similar feel, is that no matter how much you think you've planned ahead, there's going to be something new and exciting. A user has a new idea, there's some new, slightly out of bounds sample. And so you always want to make sure that on top of that, on top of the foundation, you can extend and elaborate a little bit as you go. Next slide, please. All right. So pivoting a little bit from the more abstract, I'm going to say a little bit more about the details of how we do this with, exactly how the architecture of Bluesky and some of the technical details. Next slide, please. So what is Bluesky? It's an open source Python toolbox for the data acquisition. The goal is to bridge the scientific Python ecosystems, NumPy, SciPy, scikit-learn, matplotlib, all of those into a data acquisition setup that scales both up to something the scale of a major user facility, and all the way down to bench scale of single PI labs. And to do this, we've built up a mini ecosystem of libraries that are, they're co-designed, we built them together, but they are as independent as we could possibly make them. So that kind of going from the bottom up, there's a hardware abstraction layer, which takes that control system I mentioned earlier and bundles it back into semantic objects like a thing that can move, a thing that can take data, a sequencing engine that knows how to take a series of requests of data to be collected and those hardware objects and do it, a library of the logic that actually is the data acquisition that we call the plans, a streaming first metadata rich data model that is unimpeded by data formats. So as the data is collected, it is streamed out in real time. So if you have the need for streaming real-time reduction, we can provide that. And then a growing number of library services and applications that build on everything else to provide an integrated user experience. Next slide, please. So open source is a very broad term. A way we like to think about this is this is a framing from Matt Rocklin about the stages of openness. The first stage of open source is you can say, here's some source code, but if it doesn't have a license, like you can look at it, but you can't actually use it. And as then you can provide a license so your friends can actually use it, but that's different than the next stage up is, and now taking things back, right? There's some models of open source, particularly, Google's infamous for this, where every so often they throw some code over the wall but there's no way to push anything back into it, right? You get what you get, and you just move on. There you can start doing your development in the open. So you may still be fully driving the process, but you work in the open so people can see it. At various levels of like just the work and the decisions of how you drive the work. And at the in the most robust and mature would be a multi-institutional collaborations where the stakeholders are identified as facility scale stakeholders. Our goal, not every open source project needs to drive all the way to multi-institution engagement. Like for some projects that just doesn't make sense for what the project is doing, what it's doing. However, for Bluesky, we're really trying to drive towards the finals, the multi-institution engagement. And if people are if there is more interest in bringing Bluesky to electron microscopes, we're definitely interested in bringing you on board as partners in this. Next slide, please. As I mentioned before, we're used across in the US, we're used across the DOE light sources. We're also used at Australian, the Australian light source, BESI 2, the Foang light source in Korea. Diamond light source has contributed a significant amount of effort to it over the last couple of years, and plans to use it as the baseline tool for their new for their upgrade their building. Yes, Canadian light sources started to use it a little bit along with Chess at Cornell and the Swiss light source PSI. And linked here is there's also, as I said, there's been ongoing work to bring it parts of the Bluesky stack to electron microscopes. Next slide, please. And so this is a diagram of what I believe is currently there, where you have the electron microscope on the right. And then that is directly pushing into tiled. And then on the left side being driven by not things other than the run engine. However, I think this highlights the benefit, one of our design decisions to keep the libraries and parts of the Bluesky ecosystem as independent as possible, because it allowed the adoption of parts of it, in this case tiled, without necessarily requiring buying into the full system in every single part of the ecosystem. Next slide, please. Yeah. So just saying again, like the adoption can be incremental. There is, the microscopes where the tiled adoption is coming first. At other facilities, the adoption has been OFID first. And in some cases, we've seen the adoption of the run engine, and then they re-implemented OFID on themselves because they had a very custom homegrown control system. Everything is in Python, so it is accessible to staff, facility staff and the users, because that more and more people are coming in knowing Python. And we really tried to follow the upstream scientific Python community of how distributed loose collaboration can work well. Next slide, please. So we picked Python 10 years ago, and it looks like there's been a growing bet, or there's been a good bet. Python usage continues to grow. I think it's taught in most colleges now. Can you actually go ahead 2 slides, please? I just want to highlight this slide from a keynote at the SciPy conference a number of years ago now. But it models the open source, the upstream Python ecosystem as a layered shells of more and more domain-specific libraries. So at the center is CPython itself, which is used for many things, including web development, system management, like system administration. The first layer is the core, you know, the core numeric libraries, and in Python that provide completely domain agnostic, but they do math with arrays. The next layer out is visualization, higher level structures like tables, and they can decide by more specialized functions that are only like Legendre polynomial, that sort of if you need them, you need them, but if they're not just everybody, as you go far and further out, you get more and more specialized until you get up to like SunPy is a library specifically for processing data collected from solar probes. AstroPy is focused on astronomy. Next slide, please. Right. So the technical goals we had when we started with Bluesky, the initial team were all scientists who moved over to the control side. And we were very consciously started from understanding the needs of the data reduction analysis and what metadata and ancillary data was needed for that analysis, and then work backwards to how we would collect that and ensure that was there. We wanted to be unopinionated about data formats, getting into the discussion of, HDF5 versus TIFF versus ZAR versus, Parquet versus, the custom proprietary format that comes out of your camera. We didn't think it'd be possible to drive all of our use cases to a single file format, but instead we focused on data structures. So, identifying what is an array, of how many dimensions, what should be represented as a table, and then nested hierarchical structures of those things. We wanted to support proper streaming out of the box, so that for a long-running experiment, you can provide that really immediate feedback to the user, the scientist, to say, like, is my measurement working? Right? If you can capture, if you see the data start coming up and you can see right away, oh, the sample fell off, I should not waste an hour of time, scanning empty space. That can save a lot of time for the user, and then hence, make the facility that much more productive, make that user that much more productive. Streaming also provides a interesting path to feed back into the data acquisition to drive, basically drive adaptive experiments, and that was designed in from the start. We want to be able to handle asynchronous data streams. So when you're during data collection, there's some things that you need to measure at the full rate of your detector, like the various currents, various things that need to be lockstep with your primary measurement. And there's other things that you need to measure and you need to record, but at a much slower rate. The canonical one we use for a lot is like if you've got a large copper block that is keeping your sample cool. If you're taking data at a kilohertz, it doesn't make sense to sample the temperature of your sample at a kilohertz because the thermal mass is just sufficiently large. It will never move that fast. But if your experiment's an hour long, you do need to track the temperature at something higher than the beginning of the experiment or the end. So the ability to have multiple data streams at different time rates, possibly not even on a fixed time step, was designed from the beginning. And we wanted to be able to support this multimodal experiments from the jump. Next slide, please. Slightly more, slightly zoomed out a bit. We wanted to be able to bridge from what we were doing into the very successful scientific Python ecosystem. Because it's all in Python, if you need a Fourier transform, it's just, import NumPy and you have your Fourier transform that, available to you. We wanted to be generic across science domains. At NSLS2, we started this project as the facility's coming online. So we started with 6 beamlines. We've currently scaled to 30. We have 60 ports, which is the end goal. The goal is to eventually fill them all. And within that set of instruments, there's an incredible diversity of science domains being done. So we need to be able to support all of them. And we wanted to be able to both scale up to the scale of the facility, but it's very important to us to be able to scale down to smaller instruments. So whereas at a large facility, it might make sense to have a number of a facility scale database or API gateway running. But we didn't want to make running those things to be table stakes to start trying this out and bring it to a smaller instrument. So it's important to scale. Also, the scaling down means you can develop and work on these parts in isolation without needing to stand up, the entire world to be able to debug a motion device. Or next slide, please. In addition to technical goals, we had some sociological goals. We're constantly trying to overcome non-invented heroism. Part of that is the naming. NSLS2 doesn't appear in any of the core library names because we wanted to make this easy to be adopted outside of NSLS2. As I mentioned before, the components have well-defined boundaries. And again, while they're co-developed and they're intended to work with each other, we've held very firmly to there's no direct dependencies. So if you only want tiled, you can stand up tiled, use tiled, and we think it's an incredibly useful tool, even if you don't use anything else in the ecosystem. Also taking a inspiration from the scientific Python ecosystem, we really wanted to make sure that the code we provided could be reused in new and creative ways that we didn't imagine when we started, right? The more unexpected uses this code finds, the more we think we've achieved our goal here. And finally, we want to be able to present something that, because the beamlines are each serving slightly different techniques, slightly different user communities, we wanted to make sure the beamlines could provide a very tailored and tuned experience for their users. And so next slide, please. And to that end, as you look at Bluesky, you really should have in your head, this is a toolbox of things you can reach for to build, not a a shrink wrap monolithic product that is, you drop it down and does everything. Next slide, please. All right. So I have 10 minutes left. So this is going to be, I'm going to go through this very quickly so we have some time for questions. Is that okay?
Yes, yes.
Okay. So next slide, please. So the bottom of the stack for Bluesky is called OFID. It sits between, so it sits above that generic control system, there being Epix, Tango, something custom, possibly direct access to hardware, and provides a unified high-level API with about a dozen very generic verbs. So like trigger, which means please start taking data and tell me when you're done. Set, which is please move a value and tell me when you're done. And that's the OFID layer. It bundles together parts of the control system into a coherent whole. Next slide, please. The next layer up is the orchestration engine, which we call the run engine, that basically consumes a plan, which is the set of instructions, which the OFID objects that plan works on, and then it's responsible for actually using those verbs on behalf of the user to drive the hardware to do whatever is needed to do. Next slide, please. The run engine Some of the messages you give it are please collate data and emit it. And so the run engine emits this data live as it's going, which can then be subscribed to by a number of different consumers that can do things like show you the plot as it's going, write it into storage, possibly export it out of the facility in a streaming fashion, or send it to an AI/ML agent to start chewing on and provide, then you eventually close that loop back and feed back to the run engine to drive the experiment. Next slide, please. So this is a example basically from one of those examples we wrote. It is doing an adaptive scan, not a very smart one. It's just basically looking at what the slope is and then varying the size of the step to try to sample the Gaussian. Lots of points in the middle where it's interesting, not many points out in the flats where it's boring, to try to optimize, basically finding and characterizing it. Next slide, please. The data and metadata that are emitted come out basically in JSON. There's a lightweight schema that has a minimum of required keys. So individual instruments and facilities can add in whatever they need for theirs. Small data like scalar values from a thermometer or will go directly in these documents. And for larger data like images or a long time series, there's a scheme for specifying where that file lives and how to go open it. Next slide, please. Our primary consumer of this for persistent storage now is a project called Tiled. It can consume data straight from Bluesky to then it can be fed from other frameworks because it has a documented HTTP API. In addition, it's easy to write adapters that if you have files on disk that you now want to expose with Tiled, you can teach Tiled how to understand that directory structure and files and then serve them for you. And once Tiled knows where they are, it serves them over HTTP with authentication and authorization layers as you need. That can then be consumed by Python. We have good rich clients for that in Python. We have one of our Beamline staff wrote a client in Igor to feed their existing data analysis routines. And it's HTTP. It can be served to a web app as well. Or even just like curl, you can say, please give me this frame as a TIFF and download it to your computer. Next slide, please. Right. And again, I just wanted to highlight that Tiled can serve you where your files are, but the primary usage is to serve you slices of that data and possibly transcoding it on the fly. So from the point of view of the consumer, the Tiled client, if your data is stored as HTML5 or TIFF or JPEG or CINE files or some very custom file format that your detector spits out, all the logic for going from that to arrays is handled by Tiled. And then when the client asks Tiled, please give me this slice, it just sends you just that slice. And if you tell it you understand C buffers, it will send you a C buffer and it can be copied directly into NumPy and then you're off to the races. Or if you're a web app, you can say, please give that to me as a PNG, appropriately downsampled for the size you have. Next slide, please. And Tiled also supports streaming over WebSockets. So as the run engine emits that data in a streaming fashion, it gets pushed into Tiled, and then Tiled can notify its clients that there is new data and available. And so what this is showing is we're taking data at NSLS2, just going to Tiled. There's then a process running at ALS, which is the Advanced Light Source in Berkeley. being notified there's new data, pulling it, and then running AML to provide some initial reduction of the scattering data being displayed on this laptop, which is SSH port forwarding from California back to the beamline NSLS2. In addition to, and this is done using standard HTTP technology, such as just WebSockets. In addition to WebSockets, we now Tidal also supports webhooks. So if you don't need the very granular live latency, you can still be notified reliably, like a run has finished. Please do something about it. Next slide, please. So wrapping up with Bluesky is a open multi-facility collaboration. Really think of it as a toolbox, not a single ready-to-use application that you can, in that toolbox you can use to build exactly what you need for your instrument. And the core libraries of this, OFID and Bluesky, and the document model are well established, have really been stable since about 2017. Tiled is basically stable now, and OFID async is getting very close to becoming stable as well. So this is a good time to start picking those up as tools. Areas of active development. We have been slow on providing a GUI application. A lot of the initial beamlines we built out were coming from a much older acquisition framework called Spec, which was command line driven. So that was the first thing we targeted. And we're also moving to providing GUIs and to moving more of both the control and the data access to be behind services. So making everything driven through a web app is things we're actually working on. And then finally, as I showed before, we've always had some degree of adaptive experiments. A lot of that work predated the rise of that we're currently living through of so-called AI. So making sure that we have a good handle of how to organize and implement both autonomous and adaptive scans. So you can turn the beamline, give the beamline a catalog of samples and say, please take data on all of them in the optimal way. And we also have a project called BLOP, which is really focused on beamline alignment and optimization. So I've got N optics. I want to maximize the amount of flux on my sample. Please tune all of those, and that can be a very nonlinear program, very nonlinear process. And then the thing I mentioned before is fly scanning. A lot of what there's some techniques that work very well. You change the world, you go to some position, you take data for 10 seconds, you take data for 10 seconds. But for scanning experiments where you need to, raster the beam across your sample, you can spend more time stopping and waiting at each point than you do collecting data. And so in those cases, we want to do, fly scanning, slew scanning, continuous scanning. There's all kind of names for the same thing, where you let your motors move or optics move continuously, and then as it's moving, you sample it along the way, and you can collect the same data much faster. And then as I mentioned before, just remote experiment control. So we have QServer, which is a very stable backend for remotely running a plan. We have early prototypes of what we're calling Office as a Service, which is to expose your control system securely across an HTTP API. And then that's on the backend side. And then the front end, in collaboration with ALS, we're calling a project we're calling Finch, which is React components to build standardized, heavily say standard look and feel for the widgets of building a web tool. Oh, I forgot to say next slide a couple times. So I've been talking to slides you can't see. Sorry. 2 slides forward to any questions in the 1 minute I have left.
Okay. Do we have any questions in the audience, or do we have any questions from the online participants? please put it in the chat that Thomas can see. And I had a question. So with the tiled servers, are these is the tiled server compatible with some other databases like Nomad or something?
So I'm not familiar with Nomad specifically. So but like SciCat and OnCat are things I have some familiarity with. I think so tiled is a self-contained product. It has, it has rich search on the metadata that it knows about. So it can serve some of the same functionality as other data catalogs. However, I think there's a very nice integration story where if you have a data catalog that you're already using and already serving you well, if you then enrich that to, in addition to holding a file path or a way to download the raw data, it also has basically a link to the tiled URI that said of where the user can get that data directly. And so I think that integration story works very well.
Okay, so you can use it in parallel. That's cool.
Yeah.
Thank you.
Yes.
Do we have any other questions? We have lunch served here, so I guess people are a little bit antsy to get something to eat. I just have to switch things backwards and forwards. So I have to fix it during lunch. But thank you so much for your.
Sorry, just to answer, there's a question in the text. What do you mean by single? The question is, it seems Bluesky's round engine benefits most from coordinating between multiple instruments. Is that naive? And is that worth integrating Bluesky for a single instrument? Part of that depends on what you consider an instrument, right? For us, that's a beamline. I would say that would be for my context of working with STEM machines, I would say that'd be the entire microscope. So, I think it is worth integrating because you could say, you'd have one plan which would tune all of your lenses to make sure the electrons are coming down where you wanted them, and then a set of plans for any of the techniques you would want to run. The moving the grid to the right place and then running the raster over it is a thing you could express as a Bluesky plan. If the vendor software already does that sufficiently, it may not be worth re-implementing something the vendor already provided you. Like the way I would handle that with Bluesky would say, right, there's a fly scan, which is that whole thing. And at the end, we get out one big block of the data from that raster and not try to get in there at the very granular details. But it's probably still worth integrating, at least the optics and the detectors for alignment and tuning and such. Does that answer your question? I think the benefit there would be if you had to do the same technique from different vendors, if you had basically a plan that knew how to drive that technique with vendor A and vendor B, and then the user would always do the same plan with the same inputs, and the plan would translate to vendor specific. But I think a lot of this would depend on the details and exactly where the benefits and trade-offs would come down to some details of it. So it's a little hard to give a blanket answer.
Thank you.
Okay. Thomas, thank you so much. We certainly want to use it. We'll just getting ready for that. So that was very nice. Give us an overview, and I'm glad all my team here was listening, so we know now how to bother you more. Thank you so much.
And again, I apologize for the chaos getting started and the last minute of this.